Greetings and welcome back to another Math 104 lecture. So last time when we left off, we were in the midst of chapter 2.4, which was we were talking about functions, right? So where we left off was we had just given an example of domain of functions. And again, just a quick recap, our example before was f of x is equal to the square root of x squared minus x minus 6. And we saw that we could very well get the domain of this. All we had to do was set everything that was underneath the radical to be greater than or equal to 0, because we couldn't have negatives, right? We couldn't have a negative sign underneath the radical piece here, the square root. That'd be, not allowed. So we set it to be greater than or equal to 0. We found where it was 0, which was at 3 and -2, and then we did some test points to figure out, to actually solve the inequality. And we figured out our domain was from -infinity to -2, union with the other interval of 3 to infinity. And of course, we're including those endpoints because we wanted to include when the inequality was 0. So that's where we left off with, and that was regarding domain. Now, there's another topic that's very closely aligned with domain, and that is called the range of a function. So the range of a function is similar to the domain, except instead of talking about all the possible set of inputs that you could put into a function, the range is going to describe all of the set of outputs that can come out of the function from its minimum value to its maximum value. So once again, when we write our range, much like when we write anything in an interval, we write it from its smallest value to its greatest value. So let's look at an example here. Let's say we have h of x is equal to x squared. And of course, h of x, we see it's in functional notation, right? Our function is h, and it's a function of x, right? It's not h times x. This is a function. So we have our function h of x, which is defined by x squared, with the domain. So I'm just going to write a comma here, and our domain of this function is going to be, which I'll call it set x. So our domain is going to be from 0 to 3. Okay, and what we want to do here is we want to find the range of this function. So there's a couple ways you can do it. First off, you can graph it, and when you graph it, assuming that you're only looking at the particular domain, so you're only looking at your inputs from 0 to 3, you can find the range. You can see on a graph what it'll look like, and we'll graph it in just a second here. But I want to show you guys the computational way of how to actually find the range. So what you're going to do is essentially you're going to make a table. You have your set of inputs, right? And you have your output, which is whatever your function is going to be defined by, right? So our inputs in this case are from 0 to 3. That's how we've defined the domain in this example. So that means we're going to have 0, 1, 2, and 3, okay? And of course, there are other numbers between 0 and 3. There's a half, there's 1.5, so on and so forth. There's a whole bunch of fractions. But just for the sake of graphing this, I'm only just going to pick the integers here. Okay, so from 0 to 3. And all we're going to do is, well, we're going to plug in our inputs and see what we get, right? So for 0, well, that essentially is saying, okay, well, h of 0 is equal to 0 squared, right? We learned in the last example and in the homework, when you're plugging in an input, that just means wherever there is an x, you're putting in your new input, right? So in this case, our input is 0, and wherever there was an x that defined the function, we plug in a 0. So h of 0 is equal to 0 squared, which we know is just 0. So we know then that when we plug in 0, we get 0 back. Okay, we plug in 1. So again, just to roughly show the work, and I'm not going to do it for all of them, but we plug in 1. That means we're plugging in 1 for our x, so 1 squared, and 1 squared is just, of course, 1. 2, well, that means 2 squared, so we're going to get the output of 4, and 3 squared, we get the output of 9. Now, once again, what are we looking for? We're looking for the range, and range is, by definition, the set of outputs. So that's going to be this right-hand column right here. So that's going to be the set of outputs from its least value to its greatest value. So we look at this and we say, okay, what's the least value? So that's, of course, going to be 0, and it goes all the way from 0 to 9. So I'm just going to say that my range, we could say the range, and I'll call it set y You don't have to necessarily name it, but if you just, name it, that's totally fine since I named the domain set x. So range of y, and this is going to be from 0 to 9. And that's it. All we're doing is we're describing the output now. So domain describes the possible inputs. Range is going to describe the outputs that come out of those inputs. Okay, it's fairly simple. So before we move on to graphing this, because again, I do want to show you what this looks like when we graph it, and the graph is going to seem very familiar because we've already touched on it before. What I want to ask you guys is, our domain was set in this example from 0 to 3. What happens if we increase the domain? What happens if we make it from 0 to 4, for example? So I am just going to erase the 3 here, and again, in red, we're going to make it 4, okay? And down here, well, that means we now have a new input, right, from 0 to 4. And 4 squared, that means 16. And now notice that as we change our domain, our range is also going to be impacted. So our range now is not just from 0 to 9, our range is now from 0 to 16. And sorry, that was supposed to be a curl or a bracket there. Okay. So again, notice that we changed the domain and that is going to directly impact the range, right? If we change whatever inputs are going on, we're also going to change the set of outputs that come out of that function, okay? And now let's also look one more time. I just want to change this. Instead of it being from 0 to 3 or 0 to 4, we'll put it back to 3. And instead of it starting at 0, let's make it -3 instead. So I'm just going to edit my table here. So bear with me. I just want to rewrite everything that I have written. Okay. Okay, so rewriting this, we add x, right? These are our inputs, h of x. This is our outputs. And now we're starting from -3. So -3, -2, -1, 0. But this part of the table is going to be the same thing that we already did, right? From 0 to 1, 2, and 3, right? So we know that we're going to get 0, 1, 4, and 9 here because we did that earlier. But what about the negatives? Well, again, our function is x squared, right? Our function h is defined by x squared. So that means, well, we're just going to be plugging in these other inputs into x squared. But what is -1 squared? Well, -1 squared is the same thing as 1 squared, and we get 1 back. So we get the same output that we got for plugging in 1. Okay, now we're plugging in -2. We get a +4 when we square it, right? Negatives cancel once again. And -3, we still get a +9. Now notice this mirroring that's going on here, right? We have a 9 here, we have a 9 here. We have a 4 here, we have a 4 here. We have a 1, and then of course it's the central point, the focal point of this is at 0. It's at the origin, right? So if we go to graph this, and I'm just going to really roughly sketch it. So let's say this is 3. Let's say this is -3. And when we finish plotting this, again, this is a very rough sketch, so bear with me here. And we'll say that right here is 9 on the y-axis, so x and y. The important takeaway here is that I want you guys to maintain the understanding of functions. It's totally okay for your output to be repeated, okay? So for us to get 9 twice, 4 twice, 1 twice, that's totally okay. This is still a function. What wouldn't be okay is if a particular input, so let's say 1, notice how 1 directly maps to 1. 1 is not mapping to any other input, right? So, and again, I'm just going to draw this in red to really illustrate it's not going to these. So it's not going to 0. It's not going to 4, for example. It's not going to 9. Our input only has one output for that specific input, right? -1 may also go to 1, but that's okay. We can have 2 inputs go to 1 output, and that's totally acceptable. Again, we see here that both 3 and -3 correspond to the output 9, but they're not interfering with each other. Okay, so that's really the point that I want to get here. And when we're talking about the range of this function, now that we've edited the domain, right, our domain now is from -3 to 3. Well, what's our range? Well, graphically, our range, if you want to we can of course figure out our range by looking at this column here. It's just the set of outputs from 0 to 9, which means that it's just the interval of 0 to 9, right? Which means that our range hasn't changed. Our range is still very much 0 to 9. So not everything that you're going to do to the domain will always change the range. Just be aware that it may change the range, okay? So we saw when I increased the domain from 0 to 4 instead of it being 0 to 3, that directly changed the range. However, when we added negative values from -3 to 3, just because of how x squared works, we see that our range was actually completely unimpacted. It stayed exactly the same as it was. It stayed from 0 to 9, and it was still 0 to 9 when we edited the range to include the negative values. And graphically, all you're doing here is, if you didn't have the table in front of you, you're just essentially reading it from bottom to top and seeing, okay, what's my least y value to what's my greatest y value? Well, my least y value is going to be right here at 0, right? It stops at the origin. And so my lowest possible y value is going to be at 0. So if you're writing the range for the graph, you know that you're starting at 0 here, and it goes upwards up until we hit 9, right? And once we hit 9, we stop at 9 and we're done. So that's the highest point that it ever achieves. So it goes from 0 to 9, and that would be your range once again. Okay, so that's how you would read it on a graph. This is how you would read it from a table. And just because the output repeats does not mean that it is not a function. And also, we've already talked about when you're dealing with intervals or sets or anything like that, you don't have to list the number twice just because it repeats, right? We see that we have 9 repeating. That doesn't mean you need to list 9 twice. It's just from 0 to 9. Okay? Okay. So let's go ahead and talk about graphing functions, which we already kind of just got into a little bit. So let's recall from the last lecture video, if a function f exists, so I'll write this one out. So if f exists, and f is a function, okay, then we always can draw an ordered pair from the function in the form of f of a is equal to b, which corresponds directly to the ordered pair, and they go back and forth, right? It corresponds directly to the point a comma b, or you could also think about it, and I'll put this in blue here, or as a comma f of a, right? F of a is directly equal to b here, so we know that you could just replace your output with f of a, and that's the exact same thing. Okay, so but the point that I'm making here is that you're plugging in some input, which we're going to call a here, into your function f. You get a specific output based off of that input, because that's what a function tells us, right? You plug an input in, you get one output directly back out. And because of that, we know that it corresponds to a point on a graph. Okay, so let's go ahead and look at an example here. Let's say we have some function. I don't necessarily know what the function is, but let's say we have let y is equal to f of x, right? And it's going to denote some linear graph, okay? Linear, you think line, right? So let me go ahead and draw this as accurately as possible. Okay, so we're starting with this. This is -2 here. This is -2 as well, which make that 2. We'll make this 4, and we'll make this 2, which makes this 1. And we're plotting the point here. So we have a point 4, 1, and we also have a point -2, -2. Okay, and let me break out the ruler here so that I can really make this accurate. Or as accurate as I can. Fair enough. Okay, not bad. So we have the line as it follows, right? And again, our point here is -2, -2, and our point here is 4, 1. Okay, so what I want to do for this example is I want to figure out the domain and the range of this function. Okay, I don't necessarily know what this line is, and if we wanted to, because we already know that a line is described by 2 points, we could very much figure out the equation of this line, but we don't need to. That's not, the purpose of this. All I want to do is I just want to figure out the domain and range of this function. Okay, so figuring out the domain, well, again, reading the graph, when you're talking about domain is your set of inputs, right? So when we're talking about domain, we're talking about our x-axis, okay? So that means we're reading the graph from left to right and seeing all of the possible or all of the points that are included on the graph, okay? So reading it from left to right, we see that we're starting at -2. So from left to right, we start on the x-axis from -2, and because it's a line, it's continuous, and it goes all the way up until we hit 4. So we know that our domain is just from -2 to 4. And of course, we still care about our endpoints, right? Are we including the endpoints? Are we not including the endpoints? Well, because they're dots, they're closed circles on -2 and 4, we can assume that we are including those points. So we can just say our domain, which I'm just going to abbreviate as D, is from -2 to 4. Now, similarly, if we're reading the graph like we did in the previous example and we're trying to figure out the range, now you're just going to read it from, instead of left to right, you're just going to read it from bottom to top, right? We're trying to figure out the range, which is the set of all of the outputs, so the y outputs. And so when we're reading this from bottom to top, we see that we're starting at -2, and it continues all the way up until we hit 1. Once we hit 1 on the y-axis, notice that this stops going, right? This is a line segment. We haven't, it's stopping at the point 41. It's not going on forever. So if it was going on forever, this would impact our range. But for right now, that's not our example. It's stopping at the point 4, 1. So that means that our range is from -2. It's also starting at -2, and it goes up until we hit 1. And once we hit 1, we're done. So that's it. All we're doing is we're just reading the graph first from left to right, and then reading the graph from bottom to top. Left to right will indicate your domain. Bottom to top indicates your range. Okay, so again, domain by your x values, range by your y values. Okay, so at this point, what I want you guys to do is I want you to go ahead and try your hand at the first classwork assignment, which once again is this time I gave you a picture of it, and give me a second because I'm going to try to draw the picture as best as I can on whiteboard here. Yeah, just try to figure out the domain and range of the function. Okay, so it's going to be a little bit more difficult than the one that we just did, but give it a shot, see what happens. Okay, and in the meantime, I'm just going to try to draw this as best as I can. Okay. Oops. I just realized my mistake. 1 and 1. Here we go. And we'll call that 3 right there. Okay, so I have now finally gotten to the point that I needed to get to, so we're finally good to go. So moving on with our lives here. Hopefully this wasn't terrible for you guys, but let's go through it together. So we're trying to find the domain and range of this function. And just so we're all on the same page, I'm going to label my points here. So this is -1, 3. This is 1, 3. And down here, this is 3, -1. Okay? And notice that this line here, and I'll draw the arrow a bit better. There we go. This line here is a line. It's starting from 3, -1, but it's going on forever. Okay, it doesn't have an endpoint. So please, make sure you're understanding that when we talk about the domain and range here. Okay, so to find the domain, once again, we're reading this from left to right. Okay, so reading from left to right, that means we're reading the x values left to right. Okay, so we see it's starting at -1. Okay, so that means that our domain, when we begin to write our domain, it's going to be starting from -1. And we know that we're including -1 because notice that here It's a closed circle, right? Closed circle or a closed dot implies that you are including that point. So we know that we're including that point, so we can put a bracket next to the -1. Okay, so it continues all the way down, from left to right up until we hit 1, right? Once we hit 1, we see that we have this open circle. And at 1, because we have an open circle, that means we're not including that in our domain. So we would write 1 here, it stops there, and we have a parentheses. But notice that's not the end of our function, right? We've described this parabola-looking structure, but we still have this arrow going on over here on the right-hand side. So that's still part of our function, and we need to describe that as such, okay? So continuing from left to right, we stopped at 1, but it picks back up at 3. Right? It picks back up right here at the x-axis, right at 3. So that means we put a union, just like we would normally do, because it's starting a new interval. And because we have the closed dot as such, that just means we're including 3. So we put a bracket from 3, and because it's going on forever, it just continues on, and we know that if a line goes on forever, then it's going to progress down the x-axis forever. So that means that it goes to infinity. Okay, so we see our domain from reading from left to right is from -1 to 1. We're including -1, but excluding 1, excluding the positive 1, and we're unioning that with the other interval from 3 to infinity, and we're including +3 here. Okay, so that was that, and now we have to find the range. So for the range, now we're reading the graph from bottom to top, right? So you're looking to see what your lowest possible y value is. So your lowest possible y value looks like, and I'm going to switch to blue so it's a little more apparent, looks like it's occurring right here, right at the point 3, -1. That's the lowest that the function is getting at -1. Y is equal to -1. So that means that when we go to write our range, we're going to start at -1, and we're including -1 because once again, the point is included. So we put a bracket for -1. And notice that because this line goes forever, it's actually going, this line right here, it's actually going to encapsulate all of the points that could be here, right? All of the range that could be in this parabola structure that's stopping from, it goes from, 0 to 3, right? Again, if we're talking about the y-axis, it's starting at 0 and it goes up until it hits 3, but it doesn't go any higher than 3. But because our line goes on forever, there's no endpoint to it, that means y is going on to positive infinity. So we don't need to necessarily even worry ourselves with the parabola. So that just means that it goes from -1 to infinity, and we all know that, again, whenever we're dealing with infinities, we use parentheses, okay? So the important piece here is that you're noting that you're starting from your lowest point, which is -1, and when you're reading the graph going from bottom to top, you see that, again, you have the two different pieces. You have the parabola piece going on, and you have the line piece going on, but you don't need to worry about duplicates, right? We don't care about, the output being repeated. If the output's repeated, that's okay, as long as the input isn't repeated. So because we see here that we have the 3 being repeated here and here, and at some point the 3 is also going to be repeated somewhere around here, right? That line is going to cross 3 at some point, and it's going to go on forever. Well, that's totally okay. This is still very much a function. And our range of this is basically just the range of the line, because the range of the parabola is contained within the range of the line. So we say that our range, once again, is including -1 from -1 to infinity. Okay, so let's move on here. So we have to talk also about if, trying to figure out if a graph actually is a function. Okay, so sometimes we're going to have graphs where we have to figure out whether or not that graph is a function or if it's purely a relation. Okay, so the most important rule for this is the fourth rule that we talked about in the last lecture, which is that a singular element from your input can't be mapped to multiple sets from your output. And once when we talked about that in the last lecture, we looked at the equation, for example, x squared plus y squared is equal to 1. This is the equation of a circle, right? And we saw that when we drew our circle, we had, for any particular, or for almost any particular x value, the only two exceptions are right when it's at the x-axis, right? So like right here and right here. But for all other points, excluding those 2 points, we would have some x value, which I'm just going to call x, right? And it would correspond to this point up top, but also this point at the bottom. And we knew then that that means this is not a function, right? We have one input corresponding to 2 different outputs, and that's a problem for us. Well, the easiest way that we can determine this graphically is we use something called the vertical line test. And what this means is you just take a vertical line. So I will use the ruler just so it actually maintains being vertical. You take a vertical line and you just draw it right down through your graph. If your vertical line crosses, whoops, sorry about that, did not mean to erase that. If your vertical line crosses the function, or crosses the graph, I should say, sorry, if it crosses the graph at more than 1 point, so notice that it's hitting the graph right here and it's hitting the graph right here. If it crosses the graph at any point more than once, or any 2 points on the graph, then you have a problem. Then it's not a function, okay? So we look at a circle, we see that we can draw a vertical line through a circle and it hits twice. The vertical line hits the circle twice. So as a result, this is not a function, okay? So let's look at another fairly easier example. We're going to look at y is equal to the, well, actually, before we get to that, let's start with y squared is equal to x squared. And I say to you, okay, I want you to see if you can put this in functional notation and then, try to graph it. Okay, so to try to put this into functional notation, what that means is essentially you're solving for y. And if we can solve for y, and we aren't going to get one input leading to 2 outputs, then it's a function, right? So to solve for y here, we see that there's an exponent. So we're just going to take the root of that exponent. So that means I'm going to take the square root in this case. I'm not going to put the index of 2 next to the x squared because we know it's a square root. So the square roots are going to cancel here, and we're left with y. But remember that when we take a square root, we have to put plus or minus, right? So we take y, and because y is the variable that we're solving for, I'm going to leave the plus or minus on the other side. So we have y is equal to plus or minus, and then when we take the square root of x squared, once again, same thing happens, right? The exponent and the square root are going to cancel, so we get y is equal to plus or minus x. Now notice, again, like we saw in the last homework, we can't put this in functional notation, right? We see that there's a problem. If you plug in any number for x, you're going to get 2 different numbers for y. If you plug in 5 for x, sure, you can get positive 5 for y, but you can also get negative 5 for y. So one input leads to 2 different outputs, right? And that's a problem. That's absolutely an issue. So this is not a function. And if we are to graph something like this, so if I'm going to graph y is equal to plus or minus x, right? Well, that essentially just means that we make ourselves a table of columns, right? So if I have x here, well, that means that y is equal to x. I'm just going to put y is equal to positive x here, and y is equal to negative x here. So now, again, I'll just do a short list of tables here. If I have -2, -1, 0, 1, and 2, well, then I'm going to have, for the positive values, that means that the sign is going to be entirely untouched, right? Positive of a -2 just means that, well, the negative is just going to stand out, right? Positive 1 times a -2 just means it's still -2. So then we get y is equal to -2. But over here, for the furthest right column, we're negating the -2. So we also get y is equal to 2. Okay, now we have x is equal to -1, which means it stays the same. And you can actually, kind of get a feel for this, that, oh yeah, this middle column is just going to be the exact same thing as our x's. And the right-hand column is just flipping the sign, right? So if we had a -1, it's now going to be a 1. 0, flip the sign of it, it's still 0. 1 now becomes -1, and 2 becomes -2. So let's go ahead and try to plot these pairs. And now notice that x corresponds to -2, or I'm sorry, -2 corresponds to -2, but also +2, right? So we have two different ordered pairs. We have -2, -2, and also -2, 2. So let's go ahead and try to plot some of these points. So -2, -2, I'm just going to kind of freehand this. That's going to be right about there. And then -2, +2, well, that's going to be right about there. Then we have -1, -1. So -1, -1, it's going to be right about here. And then we have -1, +1, which is right about here. Then it hits 0. So we hit 0 right here. And then things repeat, right? So then we have 1, 1. So when I say repeat, I just mean flipping. Sorry, they don't actually repeat. So then we have 1, 1 because of this ordered pair. So 1, 1, that's going to be right about here. And then we have 1, -1 as such. And so that means we're going to be right here. So 1 on the x-axis, -1 on the y-axis. And we see essentially what's happening is we're getting two intersecting lines, two diagonal lines that intersect. And just to finish this up, we're going to have a point here and we're going to have a point here. So what's really going on? Well, essentially, we're having this structure, right? Let me use the ruler. I don't want to freehand that. That was pretty bad. Sorry about that, guys. 42 degrees, not bad. It should be 45, so that wasn't horrible. Okay, so we get a structure like this where we have one line intersecting through the middle, and then we have this other line. Yeah, this one was significantly worse. Okay, line of best fit, right? So line of best fit, that's about right. Okay. Hopefully you guys don't blame me for it not being totally accurate, but that's okay. So we get these two intersecting lines, right? And once again, the way that you determine whether or not something is a function is, well, you draw a vertical line that goes through it, right? So let's go ahead and draw a vertical line. And drawing a vertical line, I'm just going to pick right here, right? And we see that when we draw a vertical line, it's going to hit our graph at 2 points. It hits here and it hits here. So this fails the vertical line test. So this is not a function. Okay? Not a function. Okay, so hopefully that makes sense to you guys. What I want you guys to do is I want you to look at your next classwork assignment, and I want you to, again, figure out whether or not the figure below on your classwork assignment is in fact a function or not, okay? And it's going to take me a little bit to graph it, so please bear with me, but I am working on it. So let me just go ahead and get started on it. But again, you're just going to be using the vertical line test to, try and see if it fails or if it passes. And really, before you try it, take a really close look at it because there is a fairly tricky element to it. Okay, so take a look at it, try to digest it, see what you come up with while I, draw it over here. Okay. I am making headway, I swear. So these are the points, -1, 0, which I will mark as such, and this is 1, 0, and then we have over here, this goes all the way up until 3 once again, and this goes from as such. And as such. Okay, so once again, don't fault me for this not looking exactly like what you guys have. There's a very, very good reason that I gave you guys the picture in your classwork assignment and that, I'm not always drawing it, but just bear with me here. Drawing it not on a chalkboard, not the easiest thing. Okay, so now we have this figure, right? And this is the exact figure that you guys have from your classwork, just it looks a little better there. So what we have to do is we have to figure out whether or not this is in fact a function. If it's a function, that means that it's going to pass our vertical line test everywhere, okay? So you might be tempted to say, okay, well, I'm just gonna, try drawing some vertical lines. So, if you're tempted to, yeah, sure, try some vertical lines, right? If we draw one here, it's only going to hit once, right? It's going to hit our line. Sure, it hits one time. Great, it's passing at that point, okay? Again, if you draw anywhere in your parabola, well, it's only hitting your parabola, right? It's not hitting your line. So sure, it's passing there, and same thing on this side. If you draw a vertical line, once again, yeah, sure, it's passing there once again. And same thing for the line on the far right. So the two problem points, the 2 points that you really have to concern yourselves are what's happening right here at this dotted line. Okay, what's going on right here? Well, notice that we're including the value -1 down here, but we're not including the value -1, 3 here. Okay, that point -1, 3, well, that's not included in our domain, right? Because notice it's an open circle. So if we were to draw a vertical line at this point, and I know it's not going to be entirely accurate, but just bear with me. So if we were to draw a vertical line right here, it's not hitting at this point because we're not including it. Again, open circle means we're not including it. However, it is hitting at this point, but that's okay. It's only hitting just the one time. So that's totally acceptable. Now, the reason this is slightly tricky is, well, what about the other side? Well, the other side, notice here that we have kind of a similar predicament, right? We see that, I'm just going to draw a dotted line here. So drawing this dotted line, we see that we have the point 1, 0, which has the x value 1, right? We care about the input more than we care about the output. If our input is repeated, then we have an issue, right? And we also have this point here, which is 1, 3, right? But notice the stark difference between the right side and the left side. On the left side, -1 was only included one time, even though this graph here goes all the way up until we hit -1, 3. We're not actually including the point -1, 3. We're saying we're getting super, super, super close, but the actual point -1, 3 is not included. So it's not going to fail our vertical line test. But here, if we actually do draw a real vertical line, well, yeah, we're going to have a big problem because we are trying to include the point 1, 3, which means we're including the input 1, and we're input 1 again down here because, well, it's a closed dot, right? Those are two closed dots on the same vertical line. So this fails our vertical line test. Even though it works for literally every other point on this graph, the fact that it fails one time means that this is not a function. So this figure is purely a relation. It is not a function. And you would just show that by drawing your vertical line at that specific point and saying, yes, this has failed the vertical line test. So this is not okay. All right. So this, again, just really reinstating this, our conflict is occurring when x is equal to 1, because when x is equal to 1, and I'll draw this out, or I'll write this out over here in plain English, when x is equal to 1, we also have y is equal to 0, but also y is equal to 3. So notice that one input is giving two different outputs, so not a function. Okay. All right, let me just get a time check here. Just want to make sure. Okay, so we're going to do a little bit more. We're actually going to start the next lecture here, the next chapter. We're going to be jumping a little bit ahead. So this is the end of chapter 2.4. And if you're following along in your textbook, we are now jumping over to 2.8. So this is composition of functions. So this is going to be a little bit more on the computational side of things, but there is going to be a graphing element in the very beginning, which is what we're going to talk about now. Okay. So composition of functions. The first thing that we have to talk about is increasing or decreasing functions, and a couple more definitions for us. Okay, so increasing, and bear with me here because it's going to seem like just complete random nonsense at first up until you see an example. And when you see an example, you'll say, oh yeah, this is really easy. Okay, so the definition of an increasing function is as follows. If you have x1 being less than x2, implying, so if this implies that your function at x1 is also less than your function at x2, then then f, your function, is increasing, which I'm going to just abbreviate as INC, which is increasing over some interval. And the interval we just define as AB. I don't know what the interval is. We don't know the numbers because this is just a general rule, right? Just the general definition, but it's increasing over some interval starting from one number to another. Okay. Also, the way that we define the interval is by the x values. So if we're saying that it's increasing over the interval, let's say from -1 to 4, we're talking about the x values, -1 to 4. We're not talking about the y values. Okay. All right. Decreasing, and I'm just going to write this in red. Hopefully you guys have this in your notes. If not, feel free to just pause here. Most of this is going to be similar, which is why I'm just going to kind of rewrite over this. So decreasing is if the difference here, if x1 is greater than x2, implies that your function at x1 is greater than your function at x2, then your function is decreasing over some interval. Again, I know this seems like jargon. Just give me a second. We'll get through the definitions, and then you can come back to these after you see an example, and it'll make more sense. Okay. And last but not least, definition of constant. So there's increasing functions, there's decreasing functions, and then there's also constant functions. And constant functions, which once again, I'm going to rewrite one more time. So in blue now. So constant is if you have x1 being less than x2, implying that your functions at both points are going to be equal, then it is constant. And again, I'm just going to abbreviate constant over some interval AB. Okay, what does this all mean? Well, just keep in mind that x1 and x2 just means that we're talking about two different x inputs. Okay, so we're just talking about on the x-axis, if we have a function, right? If the function is defined for those 2 points, if one is less than the other, implies that your output is also less than the other, then it's increasing. So what I mean by that is if we have, let's say we have some line here, and let's say we have 1 here and -1 here, right? And I don't know, I'm going to just draw some line. It doesn't have to be super accurate. Let's just draw a line like that, right? Notice how our inputs are -1 and 1, right? So -1 is clearly less than 1. We're reading from left to right, okay? So if -1 is less than 1, implies that our function, so down here, our output is less than it is here, then yeah, sure, this is increasing. And a way that you can think about increasing is, for a line anyway, is the slope positive? We already talked about this a little bit in regards to lines. The reason that we don't like to talk about slope in this case is because a function doesn't have to be a line, right? We already saw earlier in this video, h of x was equal to x squared, right? A function can be defined by many things. So just defining it by a line is not exactly accurate. So we can't really talk about slope, but you can think about slope in the same way, right? We're talking about, okay, well, if the slope is positive, then it's increasing. And in the same sense here, if our value here is less than our value here, and our line or our output is less than it is here, notice that, we're talking about the y values now, right? Output, our y values, that's what f at whatever our inputs mean. So if our y value is also less, respectively from left to right or bottom to top, then yeah, it's increasing. Okay, so an example of decreasing, again, just going to pick a line here. So picking a line is this. So for decreasing, well, this is a decreasing line, which again, we know by slope, this is a negative slope, as we can, show before. So what it means is, once again, I'm going to pick -1. I'll pick 1 here. And notice that all this means is, okay, well, my input from left to right, yeah, x1 is less than x2. But notice that now it's flipped, right? Now my output for x1 is greater than my output for x2. So that's how this is corresponding to the definition, okay? And last but not least, if we're talking about constant, well, constant is, there's actually very few times that constant is going to show up, and more often than not, it's going to be in the form of a line. So constant is where you have, so if this is your y-axis, this is your x-axis, just pretend this is a straight line, right? If you have -1 here and 1 here, and I just keep using these numbers because that's what we've been using so far. So notice at -1, we have the output right there. And at 1, we have the output right there, right? And you'd agree with me that x1 is less than x2, x1 being -1, x2 being +1. So sure, we have x1 is less than x2, but this is implying that right here, so f of -1 and f of, f of +1, these are actually equal, right? These are right along the same output for y. This is at the same line, right? The line is not changing. And so when you think about constant, this is when your slope is 0. When we already talked about this again, when we're talking about lines in particular, is okay, well, if your slope is, there's no change in y, right? Slope is defined by change in y over change in x. So if your slope is 0, that means there's no change in y. And that means that your y values are always going to be equal regardless what your input is. Okay? So it's helpful to think about this this concept in terms of slope, but as we're going to see, we're not always going to be dealing with lines, so I don't want you to exclusively think about that or think about it in that form. Okay, so let's do our first example here, and our first example is as follows. I'm just going to once again freehand this, and it is going to be another line here, so just bear with me. So let's say we have, this is -2, this is -2. And over here, so that's 2, makes us 4. We actually saw this line earlier. So from 4, and we'll say this is 1. Again, not drawn to scale, but totally okay. So -2 to -2. And again, this is 4, 1. Okay, so all I want you guys to do is determine whether or not the graph is increasing or decreasing and over what interval, okay? So over what interval means, okay, so, you know, sometimes functions can change from increasing to decreasing or from increasing to constant or whatever the case may be. So you have to always look at your x-axis and see, okay, when is it increasing? When is it decreasing? And, you know, when is it, or where is it switching, right? So in this case, we see that it's actually, you know, the function is always doing the same thing. It's always going upwards, right? From -2 to 4, 1. It's not doing anything weird in the middle. And what I mean by weird is if you had, you know, if this was -2 right here and this is 4, 1, again, just as an example, it's not doing anything like this, right? Like there's no weird stuff going on. It's just always going upwards as far as our y-axis is concerned. So because it's always going upwards on our y-axis, we know that this is an increasing function, and it's increasing on the interval. And this is why it's important to look at your x-axis here, because we're starting from -2 and we go up until 4. So we say that it is increasing from on the interval of, so I would say on the interval, but it's increasing on the interval from -2 to 4. Okay. Also, just a little semantics detail here. Notice how -2, and 4, 1 are included. When we're talking about increasing and decreasing, you don't actually have to worry about whether or not you're including the points, you know, the endpoints here. The reason for that is a little bit convoluted, so I'm not gonna like really get into it. Point is that you can actually just leave it as parentheses for your endpoints here when you're talking about, specifically when you're talking about increasing and decreasing. Okay, we're not talking about domain here. If we're talking about domain, you would absolutely need to put the brackets around it. But because we're just talking about the graph increasing or decreasing, well, it's okay to just talk about the interval, and that just means, you know, talking about the endpoints regardless if they're included or not. So the common convention is to just leave it as parentheses. Again, the reason for it is a little convoluted, but I'll touch on it really quickly. It's because when you're talking about a function increasing or decreasing, you need at least 2 points to determine whether or not something is increasing or decreasing, right? So if you only had that 1 point, if you're only talking about -2, -2, Does it really matter whether or not you are including that endpoint or not? The answer is no, because if you are not including that endpoint, if you're getting very, very, very close to -2, -2, well, that's basically just as good as if you were talking about -2, -2. So it's just common convention to just use parentheses here. Okay. Again, if you didn't understand that explanation, totally okay. Just remember common convention, just use parentheses when you're talking about increasing or decreasing. Okay, so with that being said, let's move on to a little bit more of a complex problem here. Again, the idea is I just want to see the intervals that our function is increasing, decreasing, or constant, okay? So bear with me as I set this up here. So we have our y-axis. We're going to have now our x-axis. I'm very partial to using this parabola, as we've seen now probably for, I think, the third time. So, oops, that was really not good. That's better. Okay, so we're going to have here, this is the point -1, 3. This is the point 1, 3. Then it's going to shoot downwards. And this is going to look kind of similar to what we had before. So it's shooting downwards, and then it shoots back upwards, wherever it's going. And it goes on to infinity. Okay, and this point down here is 3, -1. Okay, so the idea here, and again, I'm sorry, I should label this X and Y. The idea here is I just want to see the interval that this is increasing, decreasing, and or remaining constant. Okay, so what does this mean? Well, if we're trying to find when it's increasing or decreasing, notice that how, okay, I'm just going to start, marking things in red. The graph starts going downwards, right? We're starting from 3 on the y-axis. We're talking about our outputs, right? When we're talking about increasing or decreasing, we talk about our outputs, and it's over the interval of the inputs, right? So we're talking about our outputs, and it's starting from 3, and it goes downwards all the way up until we hit right here, which is 0. But at 0, it starts going back upwards. And the reason, again, that I don't want you to think about this necessarily in terms of slope is notice that we have a parabola-like structure here, and that's, there is no slope for a parabola. Slope is exclusive for lines. But, so it goes upwards up until we hit 3 again, and then it goes back downwards, hits -1, and then goes back upwards again. So the way that it's helpful to think about it is break this up into when it's going upwards and when it's going downwards, right? So it's going upwards at this piece right here, which I'm just going to mark with a little hash mark right there. And it's going upwards also right here, okay? So it's increasing starting from, and I'm just going to put increasing again, starting from 0. Notice how it starts from 0, right? And it goes from 0 to 3. So that's the first time that it's increasing. So I'm just going to put starting from 0 to 3. Okay? And again, don't get caught up on, whether or not you're including the point or not, because we're just talking about increasing or decreasing here. You don't need to worry about parentheses or brackets for this. Okay, so it's going from 0 to 3, and that's when it's increasing. And then the next time it's increasing is when we're starting from -1. And then, well, where is it going? Does it have a stopping point? And the answer is no, right? The function, reading from left to right, is going to end on an increasing note. It's just going to be continually increasing forever. It just goes on and on and on. So as a result, it's going from -1 to infinity. And now, when is it decreasing? Well, it's decreasing, again, reading from left to right. Well, it's starting from 3, and it goes down to 0, right? So that means that it's decreasing from the point. Oh, I'm sorry. Sorry about that, guys. Normally, I would edit the video here or, make a new video. I'm really tired. And again, making this when I don't feel great. Scratch what I just wrote for the interval. I realized the mistake I made. We're talking about the, it's over an interval of our inputs, right? So we're talking about our x values. So I made the mistake of saying from 0 to 3 and from -1 to infinity because I was looking at our y's. That's totally my fault. I apologize on that. Let me go back over this one more time. So it's increasing from 0 to 3, right? We just talked about this. Again, we're starting over. I'm talking about this hash mark right here. So it's going from 0 to 3. So what does that mean for us for the x values? Well, that means it's increasing starting from 0 on our x-axis all the way up until we hit 1. So that we would say it's increasing from 0 to 1. Okay, and I'm just going to write this in black just so we're on the same page. So it's increasing from 0 to 1. And then when is it increasing again over what interval of our inputs? Well, it's increasing again starting from 3, right? 3 is right here. So starting from 3, now this time to infinity again. Again, sorry about that, guys. I completely glossed over what I was doing here. So when you're writing your intervals, again, it's important to not make the mistake that I just made, which is exclusively focusing on your y-axis, because the y-axis is telling you when it's increasing, decreasing, or remaining constant, but it's over what interval of your x-axis that's important, right? So where is it happening in regards to your inputs? So again, increasing from 0 to 1, this piece right here, and then it's increasing again from this piece onto forever. Okay. All right. And now for decreasing, same exact idea. We see that it's decreasing here. So again, we're talking about this mark right here. So it's decreasing starting from -1 up until we hit 0, right? 0 is the turning point for our x-axis. So we say that, okay, well, it's going from -1 to 0. So, oops, -1 to 0. And then it's going to be decreasing one more time, right, at this piece right here. And when is that starting? Well, for our x-axis, it's starting at 1, and it continues to decrease up until we hit 3. So it's decreasing from 1 to 3. And now we have described the graph as far as increasing and decreasing, and that's about it. Okay? All right. How long have I been going for here? A little over 55 minutes here. Okay, why don't we go ahead and stop the video here? This is a good stopping point. We'll get into function operations and inverse functions in the next lecture. So point is, for this one, we've covered, range. We've talking about the vertical line test, and we have now talked about increasing and decreasing functions. Okay, so again, sorry about that last mistake that I just made, but I'm recording these live, so mistakes might happen. Apologies. Anyway, enjoy the rest of your day or night whenever you're watching this, and I will see you guys next time. Have a good one.